Okay, welcome everyone. Welcome to this seminar, which is the last seminar of this semester in this seminar series. It's a great pleasure to have Nisarga Paul as our speaker today. Nisarga did his undergraduate study at Harvard, working with particle physicists on the field theoretic aspect of physics, and then he did his PhD at MIT with Liang Fu. He had impressive work on marine materials and so on during that time. And he's also interested in other topics like entanglement and neural network states. And this is our topic today. Nigasa, please go ahead.
Thank you. Thanks for the introduction, Leojun, and thanks for having me. I'm happy to be presenting some recent work at this seminar. In particular, I'm going to be talking about a work titled Bound on Entanglement in Neural Network Quantum States. And also, I hope that this can serve for some of you as an introduction to neural network quantum states, if you're not familiar with them yet. And so in that spirit, please feel free to interrupt me or ask any questions at any time. Okay, so first I'll start with some background. Next, I'll move into specifically what's known and what's been studied about entanglement in neural quantum states. I'll present a bound, the main result, and I'll also talk about how one can saturate this bound. And then finally, I'll conclude. So first, for some introduction, this is, I want to situate ourselves in the quantum many-body problem. So when we're studying quantum many-body physics, we're often interested in, we have a Hamiltonian and it's acting on some many-body Hilbert space. And we could be interested in a number of things. For example, the ground state. We could be interested in the excitation spectrum and then properties of the ground states and ground state and excited states, such as dynamic or static correlation functions. And finally, we might be interested in thermal states and response at finite temperature. However, we run into an exponential wall pretty quickly in general, and brute force methods will fail at small numbers of degrees of freedom because of the exponential dimension of many-body Hilbert space. One approach around this, in some settings, is the variational approach. And the philosophy here is to restrict to a polynomially small variational subspace of quantum states, call them psi sub theta. What we have now is we can apply the variational principle, and we have the guarantee that the expectation value of the Hamiltonian in this variational state is greater than or equal to the true ground state energy. And with some physical intuition about which polynomially small subspace we should choose, we can often do quite well. For example, if we believe that the ground state should be mean field-like, then Hartree-Fock will be a good method to variationally minimize over Slater determinants. And in one dimension, for gapped ground states of local Hamiltonians, we know that matrix product states are an efficient and very good approximation to the true ground state. And we would optimize these using DMRG. So in this spirit, neural network quantum states are a new addition to the list of variational wave functions, which we can use to try to solve the ground state problem. And also, even more recently, it's been used for excited state problems, finite temperature, so on and so forth. So it's a very new and active field. The seminal work, I would say, was by Carleo and Troyer in 2017. And the simplest incarnation for a neural network quantum state is simply you choose a computational basis labeled by what I'll call X, and we parameterize the amplitudes. There are exponentially many amplitudes, but we parameterize them by some function, psi sub theta. And we could, for example, parameterize it using two real functions, one for the magnitude and one for the phase, that's alpha and phi. And neural networks will take in the computational basis label X and spit out a real number. And in that way, we've represented a quantum state. And by the nature of the neural network, we would choose to have polynomially many free parameters. So this is a polynomial class of functions. And the hope is that we've chosen it correctly so that we've captured the right part of many-body Hilbert space. And there are many architectures that are used in practice. We're not often using the simplest incarnation. Some of the names of these architectures are restricted Boltzmann machines, recurrent neural networks, RNNs, convolutional neural networks, CNNs, and transformers more recently. And they're richly parameterizable. So oftentimes, instead of parameterizing as we might have done many years ago, tens of parameters, we can be parameterizing a wave function with millions of parameters and efficiently minimizing the variational energy, even with so many parameters. So how does one efficiently estimate and minimize the energy? The go-to method is variational Monte Carlo. So pretty straightforwardly, I'm writing down a few lines of algebra that defines the variational Monte Carlo workflow. The energy estimation proceeds by taking the formula for the variational energy. We go inside the integrand, we multiply by psi, and we divide by psi. And now we can split this integrand into two factors, one of which is a positive classical probability distribution in the sense that it's all positive, p sub theta of x. And the other term, other factor, we call the local energy. And then this becomes an expectation value over a positive probability distribution of the local energy. And we can estimate this using Markov chain Monte Carlo. The energy is, after it's estimated, we want to minimize it. And we do that with gradient descent. So we need to estimate the gradient. And we do that similarly also using Markov chain Monte Carlo. And there's an expression for the gradient of the energy with respect to the free parameters theta. So throughout this talk, the free parameters of the neural network will be theta. So this is how neural quantum states are used in practice for the ground state problem. And what really motivates me to want to study and learn more about neural quantum states is its empirical success. As is the case with classical machine learning, empirical success is really the driving force. And in this case, I think it's also similar in that theoretical understanding is lagging behind. So empirically, what has neural quantum states, what have they been able to do? Ever since the seminal work, it's been shown that they can outperform traditional methods in many settings. For example, tensor networks in 2D face an entanglement bottleneck, which they don't face in one dimension. So tensor networks in 2D aren't known to be efficient. And in some cases, even as early as the seminal paper, it was shown that neural quantum states can outperform PEPs in 2D. So you see these dashed lines horizontal, which are tensor network results, and the neural quantum state result is going lower in variational energy, meaning it's strictly outperforming it on this problem. It's been extended in many different directions, even beyond lattice systems. It's applicable to continuum electrons, continuum systems. And this work on the bottom left studied the 3D electron gas Wigner crystal to Fermi liquid transition, I believe. And they showed that using an architecture called FermiNet, neural quantum states can outperform the Slater-Jastrow ansatz, which is the state of the art. Beyond ground state problems, it's been expanded in many different exciting directions: non-equilibrium, excited states, spectral functions, open quantum systems, just to name a few. And also, it's after lots of effort by many groups, neural quantum states have reached the state of the art in many hard quantum many-body problems, meaning strongly correlated. For example, the 2-DEG Wigner crystal to Fermi liquid transition, or the J1, J2 model. So for example, the specific result here was that on a 10 by 10 lattice, the J1, J2 model, neural quantum states outperformed all other methods. So this gives us some hope, some reason to believe in the power of neural quantum states coming from empirics, but there's also some theoretical reason to believe in the power of neural quantum states, at least compared to tensor networks. There was one work that showed that a neural quantum state can, in principle, reproduce a tensor network state with only polynomial overhead. The mechanism by which this was shown was called neural tensor contraction. And essentially, to compare apples to apples, one needs to isolate or unravel the tensor network into a computation into a computational graph. And the essential difficulty was to express tensor contraction in terms of neural networks, but that's possible with only polynomial overhead, it turns out, meaning a few nonlinearities per tensor contraction. And so this is captured by this cartoon over here. Neural quantum states captures some unknown part of all quantum states, but certainly is a superset of tensor network states. And in particular, what this means is that we can approximate the ground state of a gapped 1D local Hamiltonian to within epsilon by a neural quantum state of depth order log n. So this gives us further reason to believe in the power of neural quantum states. And so we're led to ask a quite general question, which is what part of many-body Hilbert space do neural quantum states capture? Before going into the entanglement perspective of the rest of this talk, I want to acknowledge and point out that it's not clear a priori what the right quantity is to study in order to quantify the power of neural quantum states. Entanglement's one perspective, and that's what I'll be talking about. But there could be other perspectives. And there's a recent work by Yang et al. From Caltech who studied the power of neural quantum states from the perspective of a quantity called conditional mutual information. They did have to restrict to sign-free wave functions, meaning they threw out the phase. But under this assumption, and under this further assumption that the corresponding classical probability distribution P of x, the norm squared, has an exponentially decaying CMI, or conditional mutual information, they were able to show that the neural quantum state can be efficiently represented by a multi-layer perceptron or a shallow short-range recurrent neural network. So they were focused on these two architectures. The condition for exponentially decaying conditional mutual information, I've written it here, essentially, it's a condition, it's a measure of correlations between two regions A and C conditioned on the outcome of measurements on a region B. And it's asking that this decays exponentially in distance between A and C. This, naively, you can think of this as saying that the probability distribution factorizes, roughly speaking. So this is an interesting result from a perspective of conditional mutual information, but it applies to two specific architectures, sign-free wave functions, and it turns out the CMI condition implies area law entangled states. So it's not it's somewhat limited from several perspectives. So it'd be nice to have a more
Nisarga,
yes.
maybe just a comment. Previously, we also had a work showing actually for ground states of gapped local Hamiltonians. The CMI actually satisfies stronger bound than the one shown here. Here, the prefactor of the exponential decay can depend on both the size of A and the size of C. Actually, it turns out it only depends on the smaller size of A or C.
I see. Okay.
And
Oh, interesting. Okay.
the size of A can be just order one.
Interesting. Okay, so it seems like this CMI condition would include gapped ground states, but possibly include more than just
Yeah,
gapped ground states.
yeah.
Interesting. Thank you. Yeah. Okay, so this conditional mutual information perspective is very interesting, and but it would be nice to have a more architecture agnostic, not limited to sign-free wave function, more general understanding of neural quantum states. So I want to focus on entanglement from here on, and I want to take as motivation primarily the area law constraint that we know for tensor network states. This really informs our understanding of tensor network states and when and if they can represent a quantum state. We know for tensor network states that the entanglement entropy of a region A satisfies a bound proportional to the perimeter of A times log of chi, where chi is the bond dimension. The area law scaling of entanglement entropy in gap ground states allows an efficient tensor network representation. And this gives us our conceptual understanding of the power of tensor networks. And be interesting to ask, are there analogous entanglement constraints on neural quantum states? And so the purpose of my talk will be to answer this in the affirmative.
Sorry, just one
Yeah.
one thing. So this efficient representability using tensor network is not always guaranteed by the area law of entanglement, right? Like in 1D, the efficient representability of MPS requires the area law of the running entropy with running index smaller than 1. And in 2D, the area law of any running entropy just doesn't seem to work to guarantee any tensor network representation.
Um, you're saying that area law entanglement does not imply efficient tensor network representation
In higher
in
dimensions, even if we
higher
consider running
dimensions.
entropy.
Yes. Okay. Yes. Okay. Yeah. I was not aware of that, but I think what I wrote down here is correct. The entanglement entropy for a tensor network state satisfies a bound given by the perimeter of the subregion times log chi, the number of bonds that you cut.
Yeah,
Yeah.
but whether this is enough, so what is the sufficient condition for a tensor network representation in high dimensions? I think this is unknown.
Yes. 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 Agreed. Mhm. Yeah. I think uh, this is an open question in tensor networks and an even larger open question in neural quantum states, whether a physical state, meaning some ground state of a local Hamiltonian, can be efficiently represented. That's an interesting question, but unanswered for neural quantum states.
Yeah,
And I want to take some steps in that direction by starting with entanglement constraints.
yeah,
Yeah. Okay, so the focus of the rest of the talk will be on entanglement. And I just want to give an impression, give an idea of the context here. So I want to discuss some works that have been done studying entanglement in neural quantum states. There's been a number of numerical works that have found interesting results. For example, there was a work by Passetti et al. Titled Can Neural Quantum States Learn Volume Law Ground States? And they found that feed-forward networks require exponentially many parameters to learn the volume law ground state of the SYK model specifically. So this was a numerical finding. I should mention at this point that there's a question of representability of a quantum state, and there's a question of if you know that it's representable by some neural quantum state, can you initialize some random neural quantum state and optimize the parameters to find the desired state? These are two separate questions, and I'm going to be dealing with the former. The question of optimization is also interesting and important, but that's probably harder and it requires different techniques. Numerically, Passetti et al. Were studying an optimization type question, and they found that it was very difficult to optimize to learn the ground state of the SYK model using the architecture that they chose. And it turns out that, in some sense, the difficulty that they encountered was primarily that of learning the fermion antisymmetry of the ground state and maybe not the volume law entanglement. So there was some work that found that a simple enough architecture that had fermion antisymmetry baked in could efficiently learn the ground state of the SYK model. So it becomes kind of, it sort of muddied the question about whether a neural quantum state can learn volume law entanglement efficiently. There have been numerous works that highlight that also not only entanglement is the relevant quantity, but also the sign structure of a quantum state and a certain computational basis. And it seems difficult in general to learn a complicated sign structure. And so all these numerical works point to some difficulty that has something to do with entanglement or sign structure or antisymmetry. And it's an important direction to disentangle, so to speak, all these different difficulties of learning quantum states. But what I'll present is a perspective on the difficulty that reference one encountered, which is that small neural networks are too simple to capture volume law entanglement. Volume law entanglement really requires a large neural network with a lot of nonlinearities. Those were numerical works. And there have also been some theoretical attempts to understand entanglement in certain neural quantum state architectures. In particular, there's been a lot of work on restricted Boltzmann machines, which have the basic form that I'm writing here, where W and H are the free parameters that are optimized. Sorry, no, W is the free parameter matrix that's optimized, and H is summed over. And this was an early type of neural quantum state that was used in the literature to show the efficacy of a simple enough ansatz to learn complicated quantum many-body states. And there's a theoretical work by Dengli and Desarma, which gave conditions for area law entanglement and volume law entanglement. And they classified the two RBMs for either case as short-range RBMs and long-range RBMs in the sense of connectivity of the hidden layer. There was an interesting work by Sun et al., which studied random restricted Boltzmann machines and proved a bound on entanglement, which was linear in the number of hidden neurons. There was a work by Gao and Duan, who constructed deep Boltzmann machine representations of quantum states generated by quantum circuits, taking this viewpoint of quantum states being in the same phase of matter if they're connected by a shallow quantum circuit as motivation. They essentially gave neural network representations of states generated by short depth quantum circuits. So this is an interesting step forward. And there was some more technical work motivated by tensor networks, trying to establish something like the simplicity of tree tensor networks for tree-like tensor neural quantum states. And just flashing in a figure here. So I don't want to dwell on the details of these works, but I do want to give the impression of the state of the of what's known about entanglement in neural quantum states. And a lot of these works deal with particular architectures. And it'd be nice to have a more architecture agnostic understanding of entanglement. So that's what I'll be presenting. And before I go into the bound or the main results, I just want to ask, what are our expectations about what neurons, what nonlinearities do for entanglement? So we can take a very broad perspective here and say that, roughly speaking, we expect that neurons and nonlinearities make for a more complicated network structure. And this should build correlations into the state, and it should also build entanglement into the state. I want to make this precise later, but as a simple example, as a minimal example, let's take a state whose amplitudes or log amplitudes are purely linear. So by definition, there are no nonlinearities in the computational graph, which would represent this neural quantum state. So let's take log amplitudes, for example, and consider a state which is defined by sum over S. Let's take S to be labeling a chain of qubits or a set of qubits. And let's just simply take log of psi of S is equal to some linear function of the plus or minus one string, which I'm labeling as bold S here. So W dot S plus B for some weights W and a bias B. It turns out that this state is too simple. Too simple to have any entanglement. It turns out to be a product state. Similarly, if you don't, I took the log amplitudes because this is typically often what's done when studying neural quantum states. But if you didn't take the log amplitudes, a similar story would hold. The entanglement is bounded by some small number, log 2. So this gives an understanding of a trivial limit when the neural quantum state is purely linear. There are no neurons. And now our general expectations could be that neurons add in entanglement as we keep building the neural quantum state. Okay, so as promised, I'll be able to make this more precise as I go forward. And at this point, I want to state the bound on entanglement. So this is a largely architecture agnostic bound. It's going to be log law in the size of the system. And it's going to be linear in the number of nonlinearities. And I'll define what I mean by what is a nonlinearity, because that's an important part of proving the bound. The statement is that under certain well-behavedness conditions on the nonlinearities, but otherwise a general feed-forward architecture, the von Neumann entanglement entropy of any subregion A is bounded by order k log n. And throughout, I'll use k as the number of neurons or the number of elementary nonlinearities. So if you want to keep in mind a simple example, you can take an MLP, a multi-layer perceptron, or a vanilla neural network of width W and depth D. And then K in that case would be simply the count of the number of neurons. It'd be W times D. And N throughout will be the number of spins. And I'll be considering discrete spin systems here with the bounded dimension of the local Hilbert space. So two things that I'll also discuss is that the scaling is tight in N. Analytically and numerically, one can show that the scaling is tight. And what I find most interesting about this bound is that it's not too loose. It's quite generically saturated. Neural quantum states are such a broad family of quantum state ansatzes, but over many variational classes of neural quantum states, this log n scaling is saturated. So this seems to be a typical behavior of neural quantum states. A corollary is that there are no neural quantum states where k is order 1 that can reach volume law entanglement. So volume law entanglement would require the von Neumann entropy to be proportional to n for a subsystem which is extensive, a subsystem which is with size proportional to n. That's ruled out for k order 1. However, while this is an upper bound, this is no reason to be pessimistic about neural quantum states. This is quite a loose upper bound. In fact, with even a few nonlinearities, it's already telling us that it can reach log entanglement scaling, which is greater than what tensor networks can reach. So this places a rare restriction on neural quantum states, but also the saturation of this bound affirms substantial expressive power. So now I'll get into the outline of how one proves this bound on entanglement. So the next few slides will be a bit more technical.
Uh, so,
Yes.
Nisarga, I have a simple question. So the idea is that the larger is the entanglement entropy, the more expressive power this, whatever the network would have. Is that sort of a equivalence between those two statements?
Yeah. Yeah, that's right. One can take the point of view that a generic quantum state has essentially a a Haar random entanglement entropy, which is volume law. So as you approach volume law entanglement, you're capturing more and more possible quantum states.
Mm,
And area law entangled quantum states, for example, are a very small part of the many-body Hilbert space.
mm,
So entanglement here is roughly a measure of capacity or expressivity, but there
mm.
could be other useful measures as well, of course.
And another corollary would be that the more nonlinearities you have in a network, the more becomes its expressive power. So nonlinearity is actually what helps the network to develop the power to capture a diversity of states.
Yeah, that's exactly right. In practice, it also seems to be true.
Mm,
Certainly from the point of this bound,
mm,
as you increase the number of nonlinearities, the bound becomes weaker, meaning it allows for larger entanglement. And
mm,
it's linear in K, the number of neurons.
mm. Okay, yeah, thank you.
So yeah, it's nice that that's, I think roughly speaking, it's pretty intuitive that the more nonlinearity you have in
Mm,
your expression for the state, the greater the diversity of states you
mm.
can capture, and particularly the larger the entanglement.
Okay.
Okay, so moving
One
on to yes, was there
question.
another question?
Yeah, so if I consider states in 2 dimensions and above, the area law entanglement is already larger than this log, right?
Hmm. Um, let's see. So
Suppose K is order
log,
1.
suppose K is order 1, then N would be, say, L squared, and where L is the linear dimension, and you'd be limited to states with log L scaling. And so indeed, yeah, that's true. K being order 1, however, is a very strict requirement. It's saying that for your entire 2D system, we allow only order 1 nonlinearities. And I guess it'll make sense when I show you what I mean by nonlinearity, but that's going to be a very simple state. If you have order L nonlinearities, which is quite typical for a study of neural quantum states, extensively many nonlinearities, you already allow area law states in 2D.
Yeah. From this
Because
bound,
K is
yeah, from this bound, if we consider a d-dimensional system, it seems K needs to be L to the d minus 1 in order to capture the area loss.
Yes, yes, yes.
Mhm.
That's right. Mhm. Okay, so I'll split the if there are no further questions about the statement of the bound, I'll split the outline of the proof of the bound into 2 steps. The first is what I'll call feature reduction from arguments about the computational graph of the neural quantum state. And the second will be taking those arguments and using a polynomial approximation for the neural quantum state. So first, what do I mean by feature reduction? To explain this, I need to lay out some facts about the structure of the neural quantum state that I'll be considering. So just making some notions precise and trying to allow for maximal generality at the same time. I'm considering a pure state on n spin degrees of freedom. You can think of it as living on a geometry or a lattice if you wish, but I'm not assuming any geometry. And there is a computational graph of this neural quantum state, which is a directed acyclic graph with nodes V and edges E. So capital V is the set of nodes and E is the set of edges. The graph is going to take the form of this image here, as an example. And it can be much more complicated in general, but essentially there are input nodes, one for every spin. There's an output node, which takes the value of the amplitude psi of s. And in between, there are nonlinearities, which are these green nodes. There are directed edges between between input nodes and the green nodes, and between green nodes and each other, but in such a way that there are no cycles in this graph, no directed cycles. The value of each node is defined recursively as sigma sub v, where sigma sub v is some scalar nonlinearity, meaning mapping scalars to scalars, of a bias plus a sum over previous nodes that are directed into this current node, plus possibly a sum over input nodes directed into this current node. This is allowing for full generality. For example, the first few nodes might entirely depend on the inputs. The W's are weights, and U of S is a previous node that is pointing into the current node. And B and the W's are all the parameters which parameterize the neural network. So this is a very general definition of a neural quantum state, and I'm setting this out because I don't want to restrict to a particular class like an MLP or a convolutional neural network or a transformer. But if you're interested in a particular neural quantum state architecture, to apply the results that I'm going to show, you'd have to unravel the computational graph and express it in this form. So that's pretty easy to do for any given case. For example, an MLP is just some rectangle of neurons with connectivity however you wish. A convolutional neural network is a special case of that. Transformers can similarly be disentangled or unraveled into a computational graph. There's a bit of a subtlety when it comes to recurrent neural networks because there's a notion of cycles in that computational graph, and one would have to unravel the recurrent neural network for t time steps and consider that as your neural quantum state in order to apply the results here. But suffice it to say, this is a quite general definition. Okay, so the key step that I want to present next is called feature reduction. First, I need to define what an affine feature is. An affine feature is a scalar of the form T of S is W dot S plus B. And I'll want to write the neural quantum state as a function of affine features alone. So I want to write psi of S in the form G of T1 of S dot 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 T mu of S for some mu. Let me point out that I can always write it in this form if I take mu is equal to n, where n is the number of spins. In that case, I would just take T1 of S to be equal to S1 and take Ti of S to be equal to Si, the ith spin value. So this could be a trivial rewriting, but it will be a useful compression whenever mu is less than n. So this will only be useful when mu is less than n. The claim is that we can achieve such a rewriting with a number of affine features mu less than or equal to k plus 1 in generality, where k is the total number of nonlinear nodes, the size of V. So this is a statement of feature reduction, and the proof is as follows. We use the fact that a directed acyclic graph has an ordering of its nodes such that if Vi comma Vj is a directed edge, then Vi comes before Vj in this ordering O. And we can prove this statement by induction on O. So first of all, V1 must be of the form V1 of T1 of S. In other words, the first nonlinear node must simply be a function of a single affine feature instead of all the spins individually. It's a function of a single affine feature. This is true by definition because there were no nonlinearities before V1, so it can only depend linearly on S. Now, V2 is the second node in the ordering, and it must be of the form some function of V1 and some function possibly of a new affine feature, T2 of S. And since V1 is a function of T1 of S, V2 is some function of two affine features, T1 and T2. So carrying on, each node can introduce one additional affine feature at most. And after k nodes, we have a function of k affine features, and then one more step to go to the output node. And we can conclude that the output node is a function of, at most, k plus 1 affine features. So that was the statement of feature reduction, and I'll tell you why it's going to be useful in a second, but I just want to pause and ask if there are any questions about the statement or the proof.
Yeah, so from my reading of your paper and the proof, this seems to be a completely general and completely true statement, regardless of any details about network construction. The only requirement seems to be that these vertices can be ordered in some fashion. So this is really a very, very general observation, which maybe people just overlooked in the past. Is that the way I should think about it?
Yeah, I think it's possible that it is completely general. We don't even need to assume an ordering of nodes. It turns out that any directed acyclic graph has an ordering. So that was a key. That's why that's why we need it to be directed. But yeah, I think it's a general argument, and I haven't seen it before, but it could be in some obscure works. I'm not sure. Yeah, it could be useful to maybe people studying ordinary neural networks.
Yeah, I have a feeling that might be the case. Thank you.
Okay, so all I need to take forward from this slide is that I can write my entire neural quantum state psi of S as G of some number of affine features, and in particular, at most k plus 1 affine features. So that's what I'll assume from here on. I'll actually keep mu separate from k plus 1. I won't assume that it's k plus 1 because in full generality, mu can be less than k plus 1. We could have some linear dependencies or something, or some neuron didn't introduce anything new. So mu is some separate number, and it's at most k plus 1. You can think of this as the dimension of an intermediate feature space. If you're familiar with some neural network jargon, you can think of this as some internal representation of the spins. So that's what I'll mean by mu. So now at this point, I do need to make some further assumptions about psi of s. And I want to argue that they're mild, and there are probably different choices that one can make at this point. But a sufficient condition is the following, some analyticity condition. I will assume that this function g, which is a function from real space, Euclidean space of dimension mu to the complex numbers, is analytic in a complex neighborhood of each of its arguments and bounded on this neighborhood in a manner independent of n. So it's well behaved, and the motivation for such an assumption is the following. If you allow your neurons to be crazy enough, you can get crazier and crazier states. So I don't want the nonlinearities to be pathological. I want them to be ordinary, like tanh or cosh or sigmoid or something like that. I want them to be analytic and bounded on a neighborhood of their domains. For example, I don't want the nonlinearities to depend on the system size. I don't want the individual neuron to become more and more intricate as the system size grows. So that's the sort of thing I'm ruling out with this assumption. So now we have a function g, which is analytic in a complex neighborhood of each of its arguments. And from classical approximation theory, we could conclude that there's a polynomial from the same domain, Euclidean space of dimension mu, to the complex numbers of degree at most d, which approximates g exponentially well in d. So the statement is that p sub d has degree at most d in each variable and approximates g on its domain to order exponentially small in the degree d. So we can turn up the degree of this polynomial as we wish. Ultimately, it'll be linear in system size that we need d to be. So it'll be linear in n. And that's the takeaway from the assumption that I placed. I use this assumption to derive some good approximation on this function g.
Excuse me, just a very basic question. If I know the function is analytic, can it not be bounded?
Um,
I'm asking why you state analyticity and boundedness as two separate conditions.
Yeah, if it's analytic, it could still have let's see. Yeah, the important thing actually is if it's analytic in some neighborhood, it will be bounded, as you said, but I also want the bound to not depend on n. So I want it to be bounded by an order 1 number.
I see. Thanks.
Yeah. Okay, so I'm going to go through this pretty quickly in the interest of getting to some further results, but I'll spend a minute
But
on this
before you go
last
on,
step.
I think
Yes.
you will eventually be able to relate the number d, the dimension of the polynomial, to n, which is the number of qubits. So should I be expecting that at some point? That d is going to be like
Yeah,
equal to n?
that's correct. The step where that becomes necessary is what I'm calling step 1 here.
Mm.
Let me think if there's a good way to explain why. I'll try to give a good explanation for why we need d to be order n.
Mm.
Yeah.
Okay.
So I want to introduce the auxiliary state, which I'm calling psi tilde, where I replace G with P, with the polynomial approximant, and I normalize it as well. So whereas psi was a sum over S G of the affine features, this state is a sum over S polynomial of the affine features. And now it turns out when you have a state that's written in such a form, it's pretty simple to bound the Schmidt rank of any of its reduced density matrices by some polynomial in the degree D. In particular, by explicit expansion and counting terms, one finds that the Schmidt rank of any reduced density matrix is bounded by something like d to the 2 mu, d squared to the power mu. We don't need the details here. Really, what this implies is that the entanglement entropy of this auxiliary state is bounded by log of this rank, which is order mu log d. So this is a result just about this auxiliary state, that its entanglement entropy is bounded by order mu log d, where mu is the number of arguments of the polynomial and d is the degree, maximum degree of each variable. Now we want to transfer this bound from the auxiliary state to the state of interest, and we need to use some standard technology here. In particular, first we want to bound the Euclidean distance between the state of interest and the auxiliary state. We want this to be exponentially small in system size. Let's see. Yeah, I think I don't have a great, let me just proceed instead of trying to explain why. We want this to be exponentially small in system size in order to then bound the trace distance between density matrices to also be exponentially small. And at the end of the day, we want to use this inequality that relates the difference of entanglement entropies to the trace distance, which I'm calling capital T, trace distance of reduced density matrices, times a log of 2 to the subregion size plus an order 1 number. And now, since we so carefully bounded the distances to be exponentially small throughout, we have that T is very small, and as a result, the whole right-hand side is going to be order 1. And now the upshot is that we've transferred this entanglement bound with the choice that D is equal to order n, and so it becomes order mu log n. And since mu is upper bounded by k, the number of nonlinearities, I'll often write this as k log n. But that's a bit looser. Okay, so here's a recap of these past few steps. So under quite general conditions, I've given a proof that neural quantum states acting on n spins with k applications of the scalar nonlinearities, meaning k neurons, satisfies a bound on entanglement, which is order k log n. More specifically, it's order mu log n, where mu is the dimension of some intermediate feature space, the number of affine features. A corollary is that this prohibits volume law entanglement for small enough neural networks. And this is consistent with some of the known numerical examples. But as I'll show in the next section, what's most interesting is that this bound is generically saturated. At least its scaling in n is generically saturated. And hence, neural quantum states generically have more entanglement capacity than tensor networks.
So I have this vague notion that introducing each nonlinearity is sort of like introducing an excitation or impurities in a otherwise very clean system. So that's kind of mental picture I'm trying to associate with your argument. And what we know from physics is that when you have a small number of these impurities, they don't interact. So we can sort of uh, consider their effects to be additive. But when you have a large number of impurities, then you cannot ignore the interactions between each impurities with other impurities. And therefore, something non-trivial starts to happen. But your result that this bound is strictly linear in the number of impurities or non-linearities seems to indicate that such sort of nonlinearity interaction is not really happening. Even when you push the k to some sort of a thermodynamic number like something proportional to n. Uh, is that a correct way of thinking about your results?
Um, yes and no. So I want to say, yeah, I want to mention one thing, which I'll get to in more detail, which is that this is an upper bound. When I said it's saturated, I meant the scaling in n is saturated, the log n. However, I don't have evidence that the scaling in k is saturated. In other words, I don't have an example of a family of neural quantum states where I increase k and the entanglement entropy increases linearly in k. I have an example where it increases logarithmically in k, which is more like what you're, it's consistent with perhaps with this intuition that maybe you keep increasing entanglement, but after some time, something nonlinear will happen, and each additional nonlinearity isn't going to add as much entanglement. So I have such an example. And so what that indicates to me is that perhaps I haven't found the most powerful architecture, or perhaps this bound is not tight in K. And I'll get to that example in a second.
Okay, thank you.
Yeah, so now I'll give some examples of what I mean but when I say the bound is saturated. So first, I want to present an analytical example just to show that log n scaling is the best that one can do in general. The example I'm giving here is what I'll call the Dickey state. It's called that in the literature as well. It's an equal weight superposition on n qubits of all the zero magnetization states. And it turns out that one can express this as a simple enough neural quantum state with a single neuron. The architecture is what I've drawn in this bottom left. The single neuron could be something that is equal to the Kronecker delta on the integers. That's all you really need. And here's an example of such a choice of function illustrated in the top right, where x is the sum of the spins. So it's the single affine feature that I've got here. In this case, you can show analytically that entanglement entropy is logarithmic in subsystem size. And so the log n scaling is the best you can do in general by proof by example here. This was a fine-tuned analytical example, but we don't need to be fine-tuned. And to convince you that this is quite general numerically, I'll introduce the...
In your Dickey state example, what is the K value?
Oh, in this example, K is equal to 1.
Oh, okay. Okay.
Yeah. Exactly. And then mu, which is, if you want to be more exact about what the bound is, it's in terms of mu, and mu is equal to 1. It's this, it's a single affine feature. Yes. So that's an example of what I'll be calling a single nonlinearity neural quantum state. And I'm illustrating the computational graph here. Simply, I have all my spins and I pass them through one nonlinearity. And I output the state, the amplitude psi, or log of psi. I'll also show some numerical experiments on multilayer perceptron neural quantum states, whose computational graphs are illustrated here, and some examples on transformer neural quantum states, where I essentially break up the input spins into patches and apply what's called the patch transformer architecture to these. And this is much more complicated than the other two. And this is just to give a feeling of a different class that's completely different and yet still shows consistent behavior. So here are the numerical results. So on the left, I'm showing subregion entanglement entropy varying subregion size with 22 qubits averaged over random initializations with some standard deviation shaded ribbons. And these are all consistent with log entanglement scaling. So the x-axis is logarithmic. On the in the middle plot, on the right-hand side, I'm showing the entanglement entropy for the subregion, which is half the system size, varying the system size n, to show the log n entanglement scaling, also a log plot, log axis, x-axis. So this shows the log n entanglement scaling at least for single nonlinearity and MLP cases. That's consistent with that in those cases. So the lessons I want to draw from this is that quite generically, for all the examples that I considered, log entanglement scaling seems quite common. at least for these small architectures where it kept k's order 1. This is favorable evidence that the bound is generically saturated, not just in fine-tuned examples. And I'm happy to discuss any details about these numerical experiments if any questions come up. But I want to end with essentially a question which naturally arises, which is that how does this align with what we know from the literature, which is that there are examples of volume law entangled neural quantum states. So as a case study, let's consider what's called the cosine net, which is a simple volume law MLP neural quantum state. Its exact definition is here, but let me just roughly say it's a linear combination of cosines of affine features. And it's been known in the literature that this can reach Haar-random volume law entanglement. This is a figure from a paper which established this. And I want to present some results now on this cosine network to show how it aligns with this bound. On the left-hand side, I'm plotting entanglement entropy as a function of subregion size on the x-axis, logarithmic scale, with entanglement on the y-axis for varying number of nonlinearities, varying number of cosines. K is equal to 1 for the bottom curve, going all the way to k is equal to 100 for the top curve. And aligning with this page curve, which is showing up as exponential here, is aligning with volume law entanglement. So it's really showing that you need to crank up k to be order system size or order greater than system size in order to reach volume law entanglement. This is a plot on the right-hand side of the entanglement entropy of some region as I turn up the number of nonlinearities. And this is what I was saying increases logarithmically instead of linearly. So this is, to summarize, what I can take away from this case study. This example has volume law entanglement only when k is very large compared to the system size, which is consistent with the bound. Also, this entanglement scaling with respect to k is sublinear, which leaves an interesting open question, which is whether this bound can be improved or whether there exists some family of states that can saturate this bound in its scaling with respect to k.
So suppose S scales with k logarithmically, it means in order to have volume law, k needs to be something like exponential in n.
Yeah, that's true. I'd be surprised if, yeah, what you said is true. I'd be surprised if you need k to be exponential in n to reach volume law entanglement.
Mm-hmm.
But I think, yeah, it's an interesting open question because my intuition for volume law entangled states comes from Haar-random states, where you have 2 to the n random complex numbers as amplitudes. And it's not going to be easy to compress exponentially many independent complex numbers into some polynomial network. At least I don't see an easy way to do it. So yeah, I think that's an interesting open question, how efficiently one can represent volume law entangled states. I don't have a proof of existence of such a state. Yeah, in fact, a lot of this was actually coming about because I found it quite difficult to write down representations of volume law entangled states using neural networks.
I see.
Okay, so running a little short on time. Let me quickly go through my my conclusion. I want to point out that what I hope I've set forth here can also be used. I hope what I've set forth here can also be used for other specific cases. The methodology seems to be quite generalizable. For example, if one was interested in a polynomial MLP, meaning each neuron is a polynomial of degree at most g, turns out that running through the same arguments, you could derive an upper bound with order 1 constants included and everything, something like w times d times log g is a bound on the entanglement entropy. In this case, this would tell you that either large width or large depth is strictly necessary to reach volume law entanglement. So this can give us a sense of when we're using the wrong ansatz for a certain problem. And in general, this work has provided hopefully a rigorous framework for studying expressivity from the entanglement viewpoint, a certain no-go for volume law entangled neural quantum states, but certainly no reason to be pessimistic, because oftentimes we're interested in area law or perhaps log law entangled neural quantum states, which this bound certainly allows, and I've shown can be generically allowed in neural quantum state architectures with even very few nonlinearities. And so one interesting question from my point of view is, what are the possibilities for very efficient neural quantum state VMC? Since we've seen that neural quantum states with order 1 nonlinearities can already reach log entanglement, can we use them to efficiently capture and simulate quantum critical states or quantum dynamics to long times? And finally, I want to leave off on the note that entanglement might not be the right complexity measure by which to understand the power of neural quantum states. It seems to be the natural language for tensor networks, but it'd be interesting to probe further in the context of neural quantum states and understand what the correct complexity measure is by which to understand their power and which part of many-body Hilbert space that they truly capture. Okay, with that, thank you for your time, and I'd be happy to take any more questions.
Thank you, Nisarga, for the very interesting talk. Do people have other questions?
Yeah. So just one simple clarifying question where you show this MLP result where the bound scales with the width multiplied by the depth. So should I think of this as the case where the number of nonlinearities is macroscopic and scales with the width times depth?
Yeah, so here the definition of my MLP was that the width is W and the depth is D.
Yeah.
So
And
I'm
how
saying,
many
so
nonlinearities?
in essence, K, what I was calling K earlier, is W times D here.
Okay. Okay.
Yeah.
Further questions? Okay, if not, let's thank Nisarga again. Thank you for the very interesting talk. So we will leave the Zoom. See you.
Thank you. See you.